Thank you for the opportunity to get to speak with you this morning. As I was preparing for what I wanted to share with you, I thought I could go into a bunch of technology, maybe bring on a couple demos or show some videos of, cool things that we're doing. I get a lot of questions about, the economics of automated driving and what's going to be happening in terms of volumes and those kinds of things. And I'll touch on that a bit. But as I thought about what I really wanted to emphasize, and I think it builds off some of the comments you've already heard this morning, is that the rate of deployment of this exciting new technology is really the topic I wanted to emphasize. I wanted to spend a little bit of time talking about some things that we can do. It'll build off of some of the comments Ian just shared with us a few moments ago. And I think this is of paramount importance for us for one very good reason, is that the faster we deploy these vehicles, the greater the likelihood that we can save some lives. So let me go into a bit of details, and I'll hit on in each of these three areas. You heard comments from Minister Clark earlier with regards to the UK. When you expand those numbers globally, about 1.3 million people died in auto accidents last year. In the US, the National Highway Traffic Safety Administration estimates that 93% of fatal accidents are caused by human error. Interestingly enough, when you dig into those statistics today, about 25% in some ways involve a cell phone and the distraction that those mobile devices cause us as drivers. Of course, much has been done over history of the automotive industry to help improve safety and reduce the number of accidents. The car manufacturers have made significant improvements. You heard a comment earlier about city infrastructure and what's happening, and the cities have dramatically improved the environment for automobiles. And of course, we've applied a lot of effort around education of drivers, right? We've tried to help reduce that human error. But the exciting thing about autonomous vehicles is that we have the opportunity to remove the human error, right? We can use technology to solve problems, and in some ways, technology is created as we've built up all of the capabilities around us. So I thought I'd dig a little deeper into each of these and go into a few examples. You heard earlier, hey, the automotive industry is well over 100 years old. If you go to the late 1800s, right, we started to introduce these vehicles. And then over time, we've begun to bring in more and more safety enhancements. Great example is airbags, right? The first airbag patent was issued in 1951, interestingly enough, just a few months apart in both Germany and the United States. But the technology wasn't robust enough to start to integrate into test fleets until the late 1970s. Commercial deployment began in the late 80s and early 90s. And it wasn't until the end of the 1990s that almost all cars in Europe featured airbags. In the US, we didn't require it until the 1998 model year. So think about that. That was almost 50 years from the invention to broad deployment of that technology. And again, I'll use some statistics from the US. The NHTSA, the National Highway Transportation Safety Administration, said in 25 years, from 1987 to 2012, frontal airbags saved 39,976 lives. So I'll give another example and talk briefly about anti-lock brakes. Very similarly, in the late 1950s, that technology was invented as well. It wasn't until 2004, though, that ABS was required in all passenger vehicles sold in Europe. Yet at the same time, ABS was found to reduce the number of rear-end collisions by as much as 38% and single vehicle accidents by as much as 33%. In fact, there was a study done by Monash University that said that anti-lock brakes integrated into motorcycles reduced fatalities by 35%. But again, 54 years from the invention of the technology until its broad implementation. And of course, then we all know about seatbelts, right? Again, three-point seatbelts invented in 1959. In the UK, seatbelts have been required since 1983. Motor vehicle safety standards took effect in the US in 1968, requiring them for all designated seating positions in vehicles except buses for some reason. So it only took 10 years to put a mandate in place, but it took 15 to 25 years when we looked at this data globally for laws to be put in place to require people to use them. So seatbelts have saved 344,448 lives in the US since 1975. But interesting enough, the studies show that more lives than that could have been saved if people would have used the seatbelts in and of themselves. So I'll shift gears a little bit and talk a little bit about city infrastructure. City managers over the last 100 years as well have been adapting their cities to allow for automobiles, right? Transforming streets, public places, making them more and more conducive for automotive traffic. And there are things today that we kind of take for granted, right? Things like traffic lights or improved road signs and even illumination, lighting throughout cities in areas where there's particular traffic congestion. So this has required planning, design, construction, as well as the ongoing maintenance of roads. And in addition, regulations that define how vehicles are maintained to keep them safe as they're being driven around in those city infrastructures. And of course, we all have to observe traffic rules. And it turns out that enforcement is the second most important requirement to improve road safety, right? So it takes a little bit of a stick there to keep us focused on following those rules. And then thirdly, I want to talk a little bit about the human factor and the importance of compliance or the lack thereof, right? Again, go back to that seatbelt example and how many more lives could have been saved had people actually taken advantage of the capabilities that were already in place. So as much as we try to educate, and I'll go back to the statistic, it's still human error that is the leading cause by far of fatal accidents. So as we think about these connected and autonomous vehicles, we have the opportunity again to eliminate the possibility for human error. But there are also a number of economic and human factors that really affect the opportunity of putting these kinds of vehicles on the road. You may be familiar with a recent Morgan Stanley report that talked about a $1.3 trillion savings that was possible in the US alone from the deployment of these autonomous vehicles. If you look at that globally, the opportunity is $5.6 trillion. And you can see some of the breakdown, right? About $500 billion from productivity gains. You think about that, productivity, we have all this time that we spend commuting, right? That we can now use productively. About the same benefit from the reduction in accidents, right? The medical bills, the lost work time for somebody who might be injured. About $150 billion from fuel savings, and again, a similar amount that can be saved just through congestion and the reduction in congestion, both environmentally as well as the cost to cities and infrastructure. And so you can look at these financial implications, they're significant. And that's taking into consideration that we can't put a cost or a value on the loss of human life. Now, I said at the beginning, I contemplated talking a little bit about economics, so I'll touch on that a moment. We get the question a lot: how big is this market for autonomous vehicles? And so, the natural thinking is, well, let's look at the number of vehicles sold this year. Let's do the projections. If we think out in time, based on the historical growth rate of automobiles, there'll be about 110 million vehicles sold in 2025. We think about some of the applications. Well, maybe there's sharing of those vehicles, right? Okay, so let's temper that forecast a bit and say it's 105 million vehicles that will be sold in the year 2025. But of course, from an Intel perspective, we think the more interesting question is, how much computing power is required to put a car on the road today and in the year 2025. So given that Intel doesn't build cars, we're one of those technology companies that won't be building cars, it's really that evolution that we care about, right? So we said, let's kind of start looking at this. If you look at cars being sold today, many have L2 level of capabilities, levels of driver assist, maybe even some starting to extend into level 3. And so there's a range of computing required, anywhere from a half a teraflop per vehicle. We add up all the computing devices in that car, microcontrollers and different types of controllers that are there, all the way up to maybe as much as 10 teraflops. We're driving millions of pixels. We have gigabytes of storage in cars. Yet there are still, in mid to high-end cars, 100 to 150 different electronic control units or ECUs in those vehicles. But now as we think forward into the year 2025 and we start bringing more driver assist and autonomous functions into the vehicles, raw computing will increase by 10x. But the number of pixels and the amount of storage will increase by about 1,000x. The bandwidth needs to increase by an order of magnitude to move all this data around in the car. But interestingly, we think there's an opportunity to reduce the number of ECUs, or those electronic control units, by as much as 2/3 as we start to take advantage of technologies that allow us to consolidate and virtualize some of the workloads or some of the computational functions that are happening. And that's at the same time as, again, increasing the amount of computing that's required by 10x. So, you heard the comment earlier from Ian about the amount of data that these autonomous vehicles will generate. And at Intel, we're focused on applications that generate massive amounts of data, because that data begs to be computed and analyzed. Now, if we look at the internet today and we think about it, most of the data in the internet is driven by us humans, right? We're tweeting a lot more today, apparently. We're taking pictures, we're sharing Facebook information, but just in the next few years, we're going to see that turnover where the data in the internet is dominated by machine data. And of course, autonomous driving is generating massive amounts of data. As we go through this development cycle, these vehicles are producing an enormous amount of data. Now that data is going to be analyzed and most of it discarded locally in the vehicle, but even that requires calculations and analysis. And then the car will decide what's important to send back up into the data center or cloud to enhance maps or to improve the artificial intelligence model that defines how all the cars on the road are performing. And so I thought maybe we could look through what's happened in other industries as they've gone through these transitions of enormous amounts of data growth, and what's happened and how they were able to take advantage of those changes and accelerate the deployment of technologies. And this is important in the context of the question that was asked earlier about creating a platform approach to how we develop and implement these kinds of solutions going forward. So, an obvious example is the PC industry, right? If we look at computing and the history of computing prior to 1980, right, the industry was highly proprietary, primarily based on mainframes. And it was the domain of researchers and big corporations and maybe a small group of hobbyists that were playing around with computers. But as that desire for personalized computing started to grow, we know the story. IBM assigned a rogue team in Boca Raton, Florida, and said, build a personal computer, do it in less than a year. And the only way they could make that happen was take off-the-shelf components, put it together with an off-the-shelf operating system, and what resulted was a very scalable, compatible type of design. And that led to a very rapid evolution of that technology and its deployment out in the marketplace. And by 1984, just 4 years later, 2 million personal computers had been sold, and we know the rest of that history. In the server industry, we've seen very similar types of things, right? In its infancy, microcomputers started filling those mainframe rooms, right? They started providing the flexibility and cost effectiveness that mainframes couldn't deliver on. But again, we started to see the implementation of more off-the-shelf components coming into that space to be able to meet the rigorous needs and deliver that centralized computing that was desired. And then, of course, what happened? The dot-com era emerged, and we started wanting nonstop operations. We wanted fast access to data. We wanted greater and greater connectivity, right? We wanted everything instantly. And then, of course, on the heels of that, the cloud era began as well. And by 2010 or 2011, the use of cloud services began to explode. And some data from IDC said that in 2011, there were 1.8 zettabytes of data generated. 1.8. By 2020, we'll be generating 40 zettabytes of data per year. So we're seeing this explosion in data there. And the way the industry has responded is create open platforms, right? Give the ability to scale and meet the needs and the desires. And as a result of that, this whole space has begun to deliver platforms as a service, infrastructure as a service, software as a service, right? And so the ability to scale and meet those requirements. And the same now is beginning to happen in networking as well. We're seeing a move to software-defined networks and virtualization of features within the features and functions within those networks to allow for scaling to occur. So if you remember, go back, I said 110 million cars shipping on an annual basis by the year 2025. We'll adjust the scale a little bit and look at the amount of computing. And in fact, we expect computing within cars to increase exponentially. And I said an L2 capable car today, about half a teraflop. Last year, let's say 80 million cars were sold globally. So it says that we put about 40 million teraflops of computing on the road with all those cars that were shipped to new customers. By 2025, we did a kind of a conservative mix of L2 through L5 vehicles being sold, and the amount of computing necessary to deliver on those capabilities says that we'll ship about 300 million teraflops of total computing. Now, of course, we're poised to be able to support that kind of computing workload. This is something, again, history has shown is certainly possible with Moore's Law. And from an Intel perspective, we're eager to take that on. You already heard an aircraft example. Let me draw a similar parallel. In the automotive industry, of course, we have lots of robust standards that define a range of subsystems. But what could we do to help move things faster, forward, increase the rate of deployment while reducing costs? Well, so I thought I would also refer to the avionics industry. They've been creating highly autonomous vehicles as well. They've had virtualized platforms. But prior to the Boeing 777, aircraft systems had a federated architecture. And in fact, every supplier bringing a new feature into an aircraft had its own electronics enclosure, a unique power requirement, unique interconnects. And what the industry started finding is they were becoming more and more limited in their ability to deliver new features and capabilities because of the limitations in space and weight and fuel costs. And so as those fuel costs began to rise, it was clear they had to change their approach, right? And so a standard emerged that allowed for the virtualization of those kinds of platforms, that allowed for common interconnects and common operating systems. It was ARINC 653. And it's allowed for the implementation of integrated modular avionics. And this has enabled them now to deliver these new features. And it was a predominant standard employed in the Airbus A380, as well as the Boeing Dreamliner 787. So as autonomous vehicles become more prevalent, as we're increasing greater mobility as a service, as vehicles are used more hours of every day, of course, safety and security are primary concerns. But we also believe that with that shared mobility on demand, the architecture and design of cars can benefit from some of these key learnings around common platforms that we've seen. So as we pursue the development of these connected and autonomous vehicles, we have the opportunity to choose that rate of technology adoption. We can continue to build proprietary systems unique to every OEM, or we can align around some best-in-class, state-of-the-art components and subsystems, like we've seen other industries do as they've scaled with the growth in data. So we have a choice to make, I think, as an industry collectively. We can go the way of the airbag. We can take 50 years to get these things deployed, or we can take advantage of what we've learned from history and work together to increase that pace of innovation. So this race to autonomous vehicles can't be done by any one company alone. It's going to take collaboration. It's going to take partnerships. We will get there much faster if we work together. And remember, this is an opportunity for us to save 1.3 million lives per year. So I thought maybe I'd conclude by also sharing a video with you to give you some perspective of history and some of the things that we're doing at Intel to help accelerate the implementation of some of these technologies.
For more than a century, the evolution of the automobile has stirred our imaginations and ignited our passions. But never in that long history has the industry faced a more important moment of transformation. A transformation that promises to bring a whole new meaning to the phrase. I wonder what this bad boy's got under the hood. The car of tomorrow will essentially be a data center on wheels, capturing and analyzing terabytes of data, collected through hundreds of sensors, and put to use by powerful in-vehicle processors. Of course, the technology that will enable fully automated vehicles won't be confined to just the vehicle itself. It will require a diverse array of flexible, sophisticated, and fully integrated solutions, from bumper to bumper inside the car, to end of the entire automotive ecosystem outside the car. The result will be a technological wonder on wheels that leverages the intelligent use of data to enable exciting new innovations, make driving safer, and completely redefines the concept of high-performance vehicle.